Okay, so we're going to get started into chapter 7, which is about probability. So 7.1 is an introduction to probability. Okay, so probability is just a measure of how likely some event is to occur, how likely it is for some event to occur. Probability for an event, in the most simplest terms, the probability of an event, probability, is a fraction. It's equal to a fraction of, it's equal to the fraction of the events, let's say this, size of event space, so we're going to talk about what the event space is, divided by size of a sample space. We'll talk about that as well, what each of these spaces are. But what I want to point out just straight from the top is when you're measuring probability, you're going to have a fraction. It's just going to be a fraction. Okay, so it's all about knowing what is the numerator, what is the denominator. Okay, some notes about probability. Probability is always between what two numbers? 0 and 1. 0 and 1. Okay. So a probability can never be negative. This fraction that we get for each problem, so we do where all the problems we do, the end result will be a fraction, which we may write as a percentage because it's very nice to see your probability written as a percentage. They will never be negative and they'll never be greater than 1. So probability is always going to be between the two numbers 0 and 1. So this whole branch of math, it's all just bounded between 0 and 1. 0, what does 0 mean? If you have a 0 probability, means whatever event you're measuring will not occur. It's impossible. Okay. If you have a 0 probability, then, like for instance, what's an example of something that will give you a 0 probability? Say you have a 6-sided die, a dice, right? A 6-sided die. You roll it. What's the probability of rolling an 8? Well, there's no chance of rolling an 8. That would be a 0 probability. A 1 means the event will definitely occur. This means the event will definitely occur. So if I roll a 6-sided die, what's the probability of rolling a 1, 2, 3, 4, 5, or 6? Well, if all of those are my options, and those are all the sides of the die, then there's a 100% chance, right? That would be 1. So recall that 0 means 0%, and 1 is 100%. 100%. So all of that work we did converting numbers to percents, fractions to percents, and decimals to percents, all of that is going to be necessary knowledge here, necessary background knowledge. Okay. Alright, at the top of this lecture I said that the probability of an event is equal to the size of the event space divided by the size of the sample space. So we still need to discuss those. We're going to discuss sample space first, and then we'll discuss event space. But before I do that, I want to say that probability is not always measured this way. This is just the simplest case. This is when all of your events are equally likely. So everything we're going to be doing in this section, the events are going to be equally likely as relative to each other. So an example of something that's all equally likely is that if you roll a 6-sided dice, your you're equally likely to roll one of the 6 numbers, right? If it's a loaded die and it tends to land on a 1 more so than the other numbers, then those outcomes are not equally likely, right? It's more likely to land on the 1, and we would need more information to calculate the probability of rolling any number. If you have a loaded die, you would need to know a little bit more information. But everything we're doing, at least in this section, going to be very simple events where the probability can always be measured just by this fraction. So all you need to know is what are those 2 numbers? What are these 2 numbers? So let's start with the sample space. What is the sample space? The sample space is just a fancy term for the list of all possible outcomes. Possible outcomes in what? Well, in a trial, in some kind of experiment, whatever I'll say a trial, whatever it is you're doing. So, like rolling a die, or flipping a coin, or picking a number, or picking a letter, whatever it might be. Now we denote the sample space as a set. Remember, sets all the way from back in chapter 2. Denoted using curly brackets, and each element in the set, so each different outcome, let me say outcome, it makes more sense here, and each outcome is separated by commas. Comma-separated list. Okay. So, for instance, the sample space for flipping a coin, what would that look like? The sample space for flipping a coin would be just 2 options, right? We would draw our curly bracket. We could use a capital T for tails and a capital H for heads. There we go. That would be it. That would be the sample space for flipping a coin. Now you notice in my probability fraction back here, I said in the denominator, it's the size of the sample space. In the jargon of chapter 2, we would say the cardinality of this set. But it's just 2, right? You just count up the number of elements in this set, or outcomes here. Okay, so that's all a sample space is. Sometimes sample spaces can get complicated to count. We're not going to get too heavy with that, but that's all a sample space is. Let's do example 1 now. Or do I want to give another example first? Let's see. Yes, let's do one more brief example before we get into the actual written example, example 1 in the notes. The sample space for selecting a card from a deck of cards. Well, this would be a lot to list, wouldn't it? This would be a lot to list. But remember, a deck of cards, if you're not familiar with it, it's got 52 cards. There are 4 suits. Each suit is, there's spades, clubs, hearts, and diamonds, and each one of those 4 has 13 cards. 2, 3, 4, 5, 6, 7, 8, 9, 10, and then Jack, Queen, King, and Ace. So there are 13 different cards, and there are 4 different colors, together making 52 different combinations of cards. So here we would say this is hard to list because I would have to figure out how I'm going to notate each one of those cards, right? And it would be a massive list. It would be 52 elements, right? So this is too much to list, but we know the size, which is usually what we want to know, the size of the sample space is 52. Okay. All right. Example 1 from the notes. Example 1 says, identify the sample space for the following experiments. Okay, and then I describe how to notate it. All right, so part A says rolling a single dice, or a die. I think it's die if it's singular. So we want to start our set brackets. A single die. Now, I didn't say six-sided die. There are many different types of dice, right? But I think I should have said six-sided die. That's a traditional die is 6 sides. So we would just say our sample space is just 1, 2, 3, 4, 5, and 6. Right? Those are the numbers that are possible to get from rolling a 6-sided die. So that's our sample space. And it turns out the size of the sample space is 6 here, because there are 6 elements. Not because the number 6 is in there, but because there are 6 elements. Okay, what about tossing 2 coins together? That's interesting. So not just tossing 1 coin, which we talked about, but tossing 2 coins. Well, how many different outcomes are there? There should be, well, let's list them. There should be double tails. There should be double heads. So I'm listing them together. These are 2 separate elements so far. Tails, tails, and heads, heads, because I'm flipping them both at the same time. And then, of course, there's tails, heads. Now, at this point, we get into a problem of, do we write heads, tails? And that's going to depend on whether or not the order of these coins matters. So if we're making a bet with someone and we're going to say, I bet that I can flip 2 coins and get heads and tails, right? Then we're going to need to know whether or not we need to count the other combination of heads and tails. So I think in this case we'll list it. We'll say heads, tails as another possible outcome. So usually whether or not you'll actually count these as 2 separate outcomes, it's going to be implied in the problem. You'll know whether or not that should be done just based off the context of the problem. C is tossing 3 coins together, okay? 3 coins together. By the way, note that there are 4. There are 4 possibilities here. How many do we expect here? Well, we could have tails, tails, tails. We could have tails, tails, heads. So 2 tails and a heads. We could have tails, heads, heads. We could have heads, heads, heads. Okay. And now we're going to get into these other combinations, pretending that these coins, that the order of the tails or heads matters here. We could have, let's see, let's make sure I get them all. This is kind of like finding all the combinations for those truth tables when you had 3 different variables. And if you recall there, 3 different variables, that's kind of the same as having 3 slots here, 3 coins, each with 2 outcomes, like true or false, but in this case it's tails or heads. If you recall from those problems, we had 8 possibilities. So that's what I'm going to look for here is 8 possibilities. So I'm only halfway there. So I'll finish the list down here. I could have tails, tails, heads, tails, heads, tails. I could have heads, heads, tails, or heads, tails, heads, or what am I missing? Heads, tails, tails. So again, from the context of the problem, we would know whether or not these 2 are counting as the same thing, because they're both 2 tails and a heads. Okay. But at the max, this is the total possible outcomes we could have for our sample space. And really, questions like that are really going to be about the event space anyways. So for your sample space, you're going to want all the different possible combinations, even if they look the same. Okay, so part D says, on an airplane you have a choice of 3 seats, aisle, middle, or window, a choice of 2 snacks, peanuts or cookies, and a choice of 3 drinks, ginger ale, flavored water, or soda. If you are only choosing one of each, so you only get to have 1 seat, you only get to have 1 snack and 1 drink, list the sample space of all the possible different combinations of these seats, snacks, and drinks that you could pick from the list. Okay. A good hint for this is to know how many combinations there are from the start, right? It would be helpful if we knew how many things should be in our list, kind of like I said here. If I knew there were 8, that's a good hint for me to know when I'm done with my list, right? So how many combinations should there be for this situation where there are 3 seats, 2 snacks, and 3 drinks? How many different combinations if I choose one of each? Well, if you make like 3 little blank spots, there should be 3 seats here, and each of those 3 different possible combinations is going to have 2 snacks, so I'm multiplying, right? Because I could have, for each one of these combos, or for each one of these seats, there's 2 possible snacks, so I could have, what were they? Aisle peanut, aisle cookie, middle peanut, middle cookie, or window peanut, window cookie, right? So that's already 6, that's coming from the product. And then again, at the end, I could have 3 different drinks. For each of those 6 there are 3 more possibilities at the end here. So what I'm saying is, if you're trying to find all the different combinations, you just take the product of those numbers. You take the product of them. So now I know the size of my sample space is 18, but what if I wanted to list them all out? What if I wanted to list them all out? So I'm going to show you a good technique here for listing multiple things out. For listing large sample spaces out, because it can be kind of tedious and it's really easy to miss something. It's nice that we know we're aiming for 18, but still, easy to miss something. So the way I would do it is I would say, starting with aisle, I would keep aisle fixed, so I'm using capital A for aisle, and then I would keep what's the first snack? Peanuts fixed. And then I would take this and cycle through my 3 different drinks. So A, P, and then where are the drinks? G, F, and S. So G. So I would say G. Then keeping A, P fixed, and then F. Keep A, P fixed, S. Okay. Now I would move on. I would keep A fixed still, because I'm not done with A. And then I would move on to C for the next snack, okay? And then I would have these same 3 drinks here, so G, AC, F, and AC, S. And now I'm going to go to the next row, which is helpful. It's nice to go to the next row when you move on to your next, when this first position changes, because now these are all my aisle seat combinations, and now I'm going to have the middle seat combinations, but it's going to be the same in these latter 2 letters here, the last 2 letters. It's going to be the same combination. So I'm going to have middle PG, middle PF, middle PS, MCG, MCF, MCS. Okay? See, once you get the first one listed out nicely, the rest of them should follow very easily. The last one is going to be that window seat. So basically just copying all of these down. With a W instead of an M. There we go. There's my sample space. It's a good technique for making large lists. Alright. So that's a bunch of examples of sample space. In the notes I say, after this example, to clarify, the trial is the process itself. The outcomes of a trial are the elements of the sample space. Okay, so for instance, with part B, the trial is the actual flipping of the coins, and the outcomes are these four elements there. Okay. Let's move on to event space now. Okay. Event space is a little bit more complicated, but it's just a fancy way of saying it's the set of things within your sample space that you want to happen. So it just depends on the problem. So first of all, event space is if you recall what subset means, like a smaller section of your sample space. It could be the whole thing, or it could be empty, or some other proper subset. Event space is a subset of the sample space. So you can see how important that set stuff is to probability. So set stuff on its own may not seem super useful in real life, but surely probability is used all the time. We do it in our heads all the time, calculating small little probabilities, but when you really want to get technical with probabilities, you need set notation. Alright, so event space is a subset of the sample space. That doesn't tell us exactly what it is. Determined by what, I didn't need that comma, determined by what the problem is asking for. So it just depends on the context of your problem. What you want to happen in a trial. Okay. So just for a quick example, an example of the sample space I gave right at the top for flipping a coin was just tails or heads. So I could say the event space. Now I wouldn't just say for flipping a coin because that's too generic, right? For my event space, I need to determine what I want, right? So the event space for getting a heads when flipping a coin is, well, flipping one coin, getting a heads, just one element in there, right? Just the heads, just H. And what's the size of this event space? It's 1, right? What was the size of the sample space for flipping a single coin? 2, right? 2. So the probability of landing a heads is 1 out of 2. Duh, right? We know that. 1/2 or 50%. Okay, so that's a super simple example there. Let's move into a little bit more complicated example, or examples in example 2, which is going to deal with coins and cards. So determine the event space for the following. Okay. Tossing 3 coins and getting at least 2 heads. Alright, so we're tossing 3 coins. So if we already have our sample space listed, it's really nice to go look at it, have it written down in front of us. Here it is. That's the whole sample space for tossing 3 coins. Every possible combination here. What we want is we want the possibilities that give us, or the outcomes that give us at least 2 heads. So that's going to be this one. That's going to be this one. That's 3 heads. That's plenty. That's going to be this one. And that's going to be this one. Okay. What's the size of this event space? It's 4, right? It's 4. Okay. What about B? B says pulling a red 5 from a deck of 52 playing cards. And I say in notes, in my parentheses, may need to explain a standard deck of cards. Okay, but I already did that. So hopefully everyone, though, is already familiar with a standard deck of cards, how it works. So we want to pull a red 5 from a deck of 52 playing cards. So I don't need to list my sample space. I know the size of it is 52 because that's how many cards are in a deck. Pulling a red 5 from a deck of 52 playing cards. Well, how many red 5s are there? Well, there are 4 suits. Spades and clubs are black. Hearts and diamonds are red. And there's a 5 in each of those. So I could say my event space is the 5 of hearts and the 5 of diamonds. That's it. So if you were given a deck of cards and asked to just randomly select a card, you would have a pretty low chance of getting either of these, right? This is a small event space compared to the size of the sample space. The sample space would be 52 because there are 52 cards. The event space is only 2. So the probability of getting one of these 2 cards would be a 2 divided by 52, which is very small percentage. Okay. We still haven't actually written down any probabilities yet. We just kind of talked about them. So let's start to do that now. So some quick notes about the probability. I've already written down the next couple parts of the notes here. Probability of an event is equal to the size of the event space divided by the size of the sample space. I'm reading through the notes right now. Question for class: what is the range of values a probability can give us? I already told you that, 0 to 1, or 0% to 100%. What is an example of an event where the outcomes are not all equally likely? So that's an example I gave earlier too, with like a loaded die. That's like a classic example of something that's not going to be equally likely to happen as the other events. So a loaded die might give you more chance of getting a 1 than any other number. Okay. Let's move straight into some probabilities. Calculate the probability of tossing 2 heads and a tails when tossing 3 coins. Okay. So the probability of this is going to be equal to the size of the event space divided by size of sample space. So we need these 2 numbers. Now, we've already got the size of the sample space because this was a problem I gave earlier. It was, so we're tossing 3 coins, right? We have to note that we're tossing 3 coins because 2 heads and a tails, that implies there are 3 coins involved, right? But how big was the size of the sample space for tossing 3 coins? There was 8, right? 8 possibilities. Now, what about the probability of tossing, 2 heads and a tails. That's our event space. But it's not 4 because it's not the same as example 2a. Example 2a asks for at least 2 heads, which allowed for this. 3 heads, right? But this problem is specifically saying, I don't want just at least 2 heads. I want specifically 2 heads and a tails. So that's going to be the 2 heads, tails, and I can have heads, tails, heads, or I can have tails, heads, heads, and that's it. That's it, right? So there's 3. So I'm not counting that heads, heads, heads. Okay, so there's my probability as a fraction. We should also always write it as a percentage too. Just remember to do it as a percentage. Just pop that into the calculator. 3 divided by 8, multiply it by 100. 37.5%. Okay. So to calculate probabilities, find your sample space, find your event space, which should be some subset of your sample space. Get a fraction, turn the fraction into a percent. Example 4. Calculate the probability of pulling a red 5 from a deck of playing cards. Okay, so I'm going to go straight into the numbers here. I already know the size of my sample space with a deck of playing cards is 52. Now, what about a red 5? Well, this is actually exactly what we did in part B of example 2. These are both the red 5s, right? 5 of hearts and 5 of diamonds. Okay. So just 2. That's the size of the event space. There were just 2 elements in that set. So almost done, right? It's once you have the size of your spaces, you're really just, it's a matter of writing them down and then just popping it into the calculator to get a percentage. It's going to be a very small percentage here. I'll say 3.8%. I'm just rounding to the nearest 10th place there for my percent. All right. Very small percentage. Let me make sure you got that if you need to pause and look at that. There's not really much else to say though. Okay, example 5. A standard 6-sided die is rolled. Find the probability of rolling a number less than 3. This is interesting. So, quickly know that my sample space is 6 because we've already talked about all the different possible combinations you can get when you roll a single die. If it's 6 sides, then there's 6 possible outcomes, right? That's the size of my sample space. What about the size of the event space? It says, and remember, your event space is going to come from what the problem is asking for. And it's asking for a number less than 3. So if you look at your sample space, so your sample space is 1, 2, 3, those 6 combinations for a die. Your event space, sample space. Your event space is just a subset of this, but a subset where the numbers are less than 3. So that's just 1 or 2, right? Not 3 itself. 3 is not less than 3. So everything above 2 is counted out. How many elements are in here? What's the size of this space? 2. Because there are 2 elements in there. All right, 2 over 6 is 33.3%. Okay. So really with these probabilities, sometimes the harder part is just counting up your sample space and your event space. Once you get the numbers down, actually calculating the probability is the easy part. Getting it to look like a percentage, that's just, 2 divided by 6 times 100 in the calculator. It's finding the size of your spaces. That can be the tricky part. And that's a matter of counting things up. And actually, there's an entire branch of mathematics that's all about counting things. It's called combinatorics. But remember that one of the rules you can use for counting is to use that product rule here, where if you have different combinations of things, just take the product to find out how many total combinations there will be. It works for the flipping a coin as well. If you didn't notice last time, how many combinations or how many possible slots are there? There are 3 because there are 3 coins. Each one has 2 possible outcomes. 2 times 2 times 2 is 8, and we had 8 total combinations there. So that's a useful technique for counting things up. Let's see what example 6 is. Find the probability of obtaining exactly 1 heads when flipping 5 coins. Okay, there we go. That's a good problem. All right. P is going to be a fraction. Okay. We want exactly 1 heads when flipping 5 coins. Let me work down here. Size of sample space. I do not want to write out all the combinations. One combination would be a string of 5 letters, like tails, like THTTT or something like that. And how many of those would there be? Well, a lot, right? So I do not want to list them all out. But I still need to know its size. Well, consider the rule I was just talking about for counting things. One outcome has 5 slots, right? 5 coins. There are 5 coins. This is like one blank outcome, right? This could be like heads, heads, tails, tails, heads, or something like that. Each one of the slots has 2 possible outcomes, right? Each one individually has 2 outcomes, heads or tails, heads or tails, heads or tails, heads or tails, etc. All I need to do is take the product of all of these. Okay, so just like for 3 coins, I did 2 times 2 times 2 to find 8 possibilities. Now I have 5 coins, I'm going to do 2 times 2 times 2 times 2 times 2, or 2 to the 5th power, right? Which is going to be 32. So without listing it all out, I know the size of my sample space is 32. Now what about my event space? Maybe we do need to list out the event space. It was finding, or rolling, or not rolling, flipping coins and getting exactly 1 heads. Think about how many different ways there would be to get 1 heads. So let's talk about the event space. So this is sample space and now event space. One possible way I could get them if I just start, sometimes it helps to just start listing out possible ways you can get just a single heads, and that'll give you some insight into how many total there will be. I could have the first one being heads and the other 4 being tails. And remember, I only want 1 heads. The second way is I could have the first one being tails and then heads and then all the other 3 tails. See what's going to happen here? The next way I could have tails, tails, heads, tails, tails. See how the heads is just scooting through, right? This isn't too bad. We can list all of these, even though I think you'll probably already figure out that there should be 5, right? There should be 5. Five different ways to get a single heads. Okay, that means the size of our event space is 5, and all that remains now is to find what that percentage is. 5 out of 32 is 0.156 whatever, then times 100, 15.6, so I'll round that to, well yeah, I'll just go to 15.6%, rounding to the nearest tenth. The problem will always tell you what to round to. If it said to round to the nearest percent, we would say 16%, because this would make the 5 round up. Whereas back here, for example, 5, if they said round this to the nearest percent, it would be 33%, because that 3 would round down. Alright, let's look at example 7. It says, Jesse. Okay, Jesse has 147 songs on a playlist. He's categorized them in the following manner. Okay, so he's got a bunch of different categories. How many? Jazz, hip-hop, folk, rap, country, and gospel, and Latin American. So, if Jesse begins listening to his playlist on shuffle, what is the probability that the first song played is a folk song? Okay, that's cool. Alright, so we have 147 total songs. What number do you think that's going to be in our probability? It should be the sample space, right? This is the size of sample space. Because that's all the songs he has. When he shuffles them, it's going to get 1 out of these 147, right? Now, they want to know what... To find the event space, we need to see what the problem is actually asking for. And it says, if he shuffles his playlist, what is the probability that the first song played is a folk song? How many folk songs were there? 13. Since this is what they're asking for, and they're asking about the first song, this is going to be the size of the event space. So it's just about pulling these numbers out. All those other numbers didn't matter. They were just different categories that are making up the rest of this 147, right? But we want to know what is the probability that he'll choose, or the program, the shuffling, will choose a folk song. That'll be 13 over, so P equals 13 over 147. So I'll approximate that to a percentage. 13 divided by 147, then times 100, 8.8%. I should really be saying approximately on these percentages. If I'm rounding, I should say approximately. 8.8%. Cool. What would be the probability of selecting the first song being a country song? Well, you would do, there are 29 country songs, so 29 divided by 147 would be much higher. It'd be like 19.7%, because there's a lot more country songs than folk songs. Okay. So that is, I actually did say how to round in this. It says, express your answer as a fraction in lowest terms. Okay. Is this in lowest terms? Well, 13 is prime. Does 13 go into 147? We can just divide real quick to find out if it can be reduced. Nope, definitely not. And then I say to set it at lowest terms, or a decimal rounded to the nearest millionth. Okay, I'll do that just so you guys know how to round that way. So if I wanted it as a decimal, now typically you're going to want your probabilities as percentages, but if I wanted it as a decimal rounded to the millionth position, that would be 0. Let's see, 0, that's the 10th, 100th, 1000th, and then 435. That's 1000th, 10,000th, 100,000th, millionth, and I lost track. Okay, let me find my place in my calculator. 88435. The next digit is a 3. Since the next digit is a 3, I would just chop all those off, zero them all out, round down, so that this stays as a 5. So that would be rounding to the nearest millionth position. 10th, 100th, 1000th, 10,000th, 100,000th, millionth. Good. But usually the percentage is preferred. Alright, that is it for 7.1. I've got some problems listed from the text for you to try. That's it.